Okay, welcome back. As I said last time, we left off here and I had asked you to answer these questions on your own. What type of charges do protons and electrons have? Hopefully this was easy. This is a review from the units that we did last semester in the first part of the year when we talked about atoms. Okay, protons have a positive charge, electrons have a negative charge. What is the law of conservation of charge state? All the laws of conservation say the same thing. Okay, they say whatever it is, like so matter, charge, momentum, whatever it is not lost or gained, created or destroyed. They can transfer or change form. So electric charge cannot be lost or gained, created or destroyed. It can be transferred from one object to another. What is an electric field? And how do they apply to objects? Okay. It's like a magnetic field that surrounds anything with an electric charge. So things that get inside that field are affected by it, like we saw with the electroscope, like we saw with the video where the man ran the electricity through the wire, and then it affected the magnetic filings, the iron filings. Three ways that charge can be transferred. Okay, conduction or direct contact is the movement of electric charge by touching or rubbing. Induction is a charged object causes a rearrangement on a nearby object. So, things that get inside that electric field are affected by the electric field, and the charges start to move depending on if the field is positive or negative. And in static discharge is when a whole bunch of electrons move all at once. So like if you have a bunch of static electricity and you touch a conductor like a doorknob, the static will discharge, the electricity will discharge from you to the doorknob, and then you'll feel that shock. Okay. Grounding is important for homes. It's directing electric charge into the ground. So like if a bunch of lightning would hit your house and it went into the wires of the house, it can damage everything that's plugged in. But by capturing lightning in the conductor and sending it into the ground, you can protect the home. Okay. Conductors move heat and electricity easily, while insulators do not allow heat and electricity to easily flow. All right, so now so far we just talked about electric fields and electric charges building up on things. And early, that's mostly what people studied when they studied electricity. It took a while for us to realize that we could run it through wires. So, when we talk about electric current, it's just like, a current in the ocean or a current in a river. It's the actual flow of the electricity. And this is what we use. It's really useful to get things done in the 21st century. So electric current is the moving of electrically charged particles. And usually those electrically charged particles are electrons. So electrons, electricity, that's where they came from. Okay, now there's a couple of different ways electricity is measured. And first, the overall flow of the amount of electricity is measured in amperes. We're going to take a look at this short clip on electric current.
Current electricity. So far we learned that static electricity doesn't move. Once the electron transfers, it stays put. That's why static electricity is not very useful. However, an electrical charge that can be made to move in a continuous stream or current is used all the time. When electrons move, we call it current electricity. Current electricity is the electricity we use every day to produce different forms of energy, such as light, heat, or sound. In order to get an electric current flow, electricity needs a complete path or circuit for the electrons to travel. Electric circuits are made up of several components. One of the components needed to make a circuit is a source of electric energy, like a generator, a power plant, batteries, solar panels, or turbines. Another part of a circuit is called a load, which is an output device, such as light, bell, or motor. Every circuit also needs a conductor. Most metals, such as copper or aluminum, make good conductors. In this demonstration, we are going to use copper wire. Using this battery as a power source, the bell as a load, and this wire as a conductor, we are going to set up a simple circuit to show you how current electricity works. First, if you look on the battery, you'll see there are two terminals. One is charged positively, designated with a plus sign. The other terminal is charged negatively, represented by a minus sign. You can start an electric current by attaching a wire to one of the terminals, then to the load. The circuit will be complete when the negative and positive terminals of the battery are connected, and the bell should ring. As long as the electric current is complete and the battery has energy, the bell will continue to ring. When the circuit is broken, the bell will stop ringing immediately. Now there is one other component that is a part of most electric circuits. It's a control device, such as a switch that controls the flow of energy to the load. Watch what happens when the switch is attached to our electric circuit. See here, the switch is open, and the circuit is broken, so the energy cannot flow. But when the switch is closed, the circuit is complete and the bell rings.
And as I said, usually the amount of, and they pointed out in the video, the amount of electricity flowing, it's measured in amperes. And a lot of times we just call that amps. Okay. And this is the rate of the flow of electricity, or how much comes out in a certain amount of time. More amps means more electricity is flowing. So if in your house you go down and there's usually a big gray box with a bunch of switches in it, they're called circuit breakers. Each one of the circuits has a certain ampere rating. It says how much electricity is allowed to flow through that circuit or that path in the house. And the more the amperage, the more electricity flows through that circuit. And the next way electricity is measured is voltage, which is the push or the pressure that makes the electrons move. Okay. And it's measured in volts. Okay. And it's considered the pressure or the push of the electrons. So a battery creates a difference in charges, giving it a push to move. The bigger the voltage means the more push or pressure. So if we think like, you can make an analogy between electric current and water. So like you could have two hoses, let's say with high pressure. You got like a garden hose, and maybe you have a high pressure nozzle on it. Then you got a fire hose, and it also has a lot of pressure. So we would say that they both had the same amount of volts. But the ampere would be how much water comes out of the two hoses. Well, a whole lot more water is going to come out of the fire hose than is going to come out of the garden hose. So in the analogy, the fire hose would have more amps, okay, and they both would have a lot of volts. Now, let's say you had two identical garden hoses. One of them you would hook to a pressure washer, and the other one you didn't have any nozzle on, you just let the water run out. But they would both let out the same amount of amperes. The amount of water coming out of the two hoses would be the same. But the voltage or the push, the pressure, would be much greater when it comes out of the power washer than when it just comes out of the hose with no nozzle on it at all. So, to think about this, one is the amount and the other one is how much pressure. We're going to take a look at this short clip on voltage and amps.
Volts and amps. Now all this electrical equipment needs a certain amount of electrical energy at a certain rate. Therefore, it is important for people to be able to measure and control an electric current. All circuits, regardless of their size, need energy and a force to drive the current. The force is called an electromotive force, and it gets the electrons moving. The amount of force the battery pushes out is measured in units called volts. The more energy a power source can give, the bigger the voltage. You'll notice that the batteries are labeled with the amount of voltage they produce. Here's a 6-volt battery and a 1.5-volt battery. Generators at power stations can push out 25,000 volts or more. That's much too powerful to use in a home. So along the way, the voltage is stepped down at a step-down substation transformer. Electricity that is used in homes is typically 110 volts. Now, as electricity flows along a wire, scientists are able to measure how quickly it is traveling through the circuit in units called amperes. The amperage, or rate at which the electricity current flows, depends on two things. The first thing that determines the flow of electricity is the voltage of the power source, and the second is how well the circuit conducts electricity. Remember, a conductor is any material through which electricity can flow easily. Some materials do not conduct electricity well, and they're called insulators. Which materials are good conductors, and which are good insulators? Let's experiment and find out.
Now, electricity flows, there's friction, just like everything else. So as it goes through the wires, there's some resistance or opposition to its flowing. Remember, friction was a force that opposes motion. Well, we have resistance, which is the tendency of a material to oppose the flow or the motion of the electrons. So resistance is like electric friction. So as electricity flows through things, there's some friction. And remember, one of the things that friction creates is heat. So things like on the top of a stove, those burners that are shaped round, they have a lot of resistance on purpose. So they create heat when the electricity flows through it. Usually we try and minimize resistance in wires and things that we use because we want the electricity to get from the source to whatever is going to use the electricity, like your dishwasher or the refrigerator. We don't want to produce a whole lot of resistance in the wall and have hot wires. That's not why you have the electricity. So it changes the electrical energy into, over here to remind us, it's electric friction, and friction causes heat. Okay? And it changes electrical energy into thermal or radiant energy. All materials have some resistance, and resistance is measured in ohms. So sometimes you see this little Greek letter in the back of things when you look at them, and it tells how much resistance is in it. Okay. Making wires thin makes it narrow and harder for the electrons to flow, so they have more resistance. Making the wires longer, there's more surface area for the electrons to travel, and that increases resistance. Making the wires hotter, okay. Atoms in the wire move faster, getting in the way of the electrons moving because they're vibrating, and the electrons have a harder time flowing through. So hot wires have more resistance. Very cold wires become much better conductors. They do a lot of experimenting at very cold temperatures, trying to make these superconductors with a minimum resistance. When the electricity flows through these wires, okay, what people want is a circuit, okay, which is a closed or complete path for the current to travel. If there's a break, the electricity will stop flowing. So like an example of water, okay, it'd be like a hose with a leak in it, okay, there's not going to be any, it's not going to get around, if there's a break. Okay, so here we're going to kind of formalize the analogy that we've been using. You think about electricity like a water hose and a pump. The amount of water flowing is the amperage or the current. Bigger the hose means more water. So, if you have like a fire hose versus a garden hose, there's going to be more water flowing through those two hoses. That's equal to the amount of amps or current. Okay. Voltage is how fast or how much push, how much pressure there is. So, another example of this, which is kind of a good one, is like the thing that the dentist uses to clean your teeth, water pick. It has a lot of pressure, but there's not much water flowing. Okay, so it would be like high voltage, but low amperage. So it has a lot of pressure, because you can blow the the dirt off your teeth, okay, while it's trying to clean them, it has enough pressure to do that, but there's not much water there, okay? He's not trying to drown you. So that would be an example of high voltage, low amperage. Now, something like a pressure washer, there's not a whole lot of water coming in the nozzle of the pressure washer. So the voltage is huge, but the amperage is small. Okay? More pressure means the faster the water shoots out, the faster the electrons are moving. The pump gives water pressure, like a voltage difference. The larger the pump means more water pressure, the faster they flow. So like when we look at batteries, they say like 12 volts in a car, a little, AA. So they don't have a whole lot of push. Okay, so low voltage means low push. Battery creates a difference in charges, giving it a shove to move the flow from positive to negative. The bigger the battery, more amps or more, there's more amps or more push. Okay, so it kind of depends. The bigger the battery can either produce more amperage or it can produce more voltage. So let's take a look at the three things we've learned about electricity down here. Voltage is the amount of pressure. So, if you put a high pressure nozzle on here, or this was a power washer, it would have a lot of volts. You just let the water run out. Okay, the same amount of water could come out, but it would be low pressure or low volts. Current is the amount of electricity that's going to flow. So, the size of the hose, the bigger the hose, as long as they have the same pressure, more water is going to come out. And then resistance is like a little friction. So it seems to slow down the flow of electricity. So like in this example, they put some sand and some obstacles in here to slow down the flow of the water. So that will create electric resistance and friction. Okay. So voltage can be really high pressure, like a wire at the dentist, or low pressure, like a drain pipe. Okay. Current can be a lot of water flowing like a fire hose, or a small amount like a water pipe. Both of these could have high pressure. They both could have high voltage. They would have a different amount of current flowing. And then friction, the electric resistance, creates heat. And sometimes that's done on purpose, like those little coiled wires and blow dryers that heat up, or the coils on the stove. We're going to stop here. I want you guys to answer these questions on your own, and we'll pick up here when we continue next time. I hope you're having a great day, and we'll see you soon.